Now we're going to talk about asymptotic notation, also known as big O notation. So, as you may have started to conclude from the previous video, exact analysis is usually more trouble than it's worth. Figuring out the exact number of time steps that each line takes can get kind of finicky. Sometimes you need to know about things that your language is doing under the hood. It's easy to miss steps, like the way the while loop has to get evaluated one extra time. And fundamentally, the RAM model is already a massive simplification. So exact analysis isn't that exact. It's never going to tell us exactly how long our program will take to run. So there aren't that many situations where we care about the exact number of time steps, but we don't care about all of the other things that the RAM model is abstracting away. In practice, when we're talking about algorithmic improvements, we're talking about order of magnitude improvements. An extra time step here or there will really come out in the wash. So it would be great if we had a way to just talk about the part of the time complexity that actually matters. Fortunately, we do. It's called asymptotic notation. And it's exactly that. It's a language for talking about the order of magnitude of the growth rate of the algorithm's time or space complexity. The formal mathematical definition of big O is that f of n is big O of g of n if there exist positive constants c and n naught such that f of n is less than or equal to c times g of n for all n greater than n naught. Okay, so informally what that means is that if f of n is big O of g of n, f of n grows no faster than g of n. So we can think of the growth rate of g of n as an upper bound on the growth rate of f of n. Note that g of n itself may not be an upper bound on f of n, because we're allowed to multiply it by a constant to get it to actually be higher than f of n. Also, because it's okay if early on f of n actually is higher than g of n, even with the constant, as long as that doesn't happen at values of n greater than a certain value, specifically n naught. Okay, so here's an example. We can say that this function in red here, n squared plus n, is big O of n squared. That means that its growth rate is dominated by the n squared term. The plus n part is going to come out in the wash. Let's imagine that n is 100. That means n squared is going to be 10,000. Once you're at that scale, 10,000 is so much bigger than 100 that the 100 doesn't even matter. And the contribution of n to the size of this function will just keep getting smaller and smaller. So that's why putting an additional constant out in front of the n squared term allows us to ensure that our bounding function is always going to be higher than the function that we're bounding. Of course, n squared by itself is not going to be larger than n squared plus n. But by multiplying it by a constant, we can ensure that past n naught is always above the function that we're trying to bound. Just to briefly elaborate on why the definition of big O is set up like this, let's think about those two parts. So why do we have n naught? There are kind of two reasons here. First of all, it's really not the small n side of the function that we generally need to be concerned about. It's okay if for small n, the function takes much longer than you would expect given that size, because generally the real issues are going to occur when we get to large n's. I don't want to say that's always the case, but I struggle to think of a counterexample. The other reason n naught is there is that a lot of functions just kind of act funky at very small values. So for instance, with n squared on the previous slide, you saw that below 1, things were acting a bit different. So when we're showing that a function is big O of another function, we have this n naught term so that we can just not worry about anything strange going on the small side of the function. Okay, so the other component is c. We know anything constant is going to come out in the wash. Constants are just not the things that are going to be dominating growth rates, because by definition, a constant is not contributing to the growth rate. Our goal is to measure the rate of change, not the absolute value. The other thing that's nice about having the c here is that it lets us potentially show that the same function can be both an upper and a lower bound. And that tells us very precisely what complexity class the function that we're looking at is. On that topic, so far we've been talking about big O, which is an upper bound on the growth rate of a function. But there are two other concepts that fall under this umbrella of asymptotic notation. The next one is big omega, which is a lower bound. It's defined exactly the same way as big O, except that C times G of n needs to be below F of n for all values greater than n naught. And lastly, we have big theta, which means that a function is a tight bound on another function, so that it can be both an upper and a lower bound. And so that's exactly what I was just talking about, where potentially by choosing different constants to multiply the same function by, we can achieve both a lower and an upper bound, thus very tightly constraining a function to a complexity class. Okay, so that's your crash course / review of asymptotic notation. To make sure that you fully grasp these concepts, think through these practice questions.